See, we were trying to understand how the lift is generated through a reaction between body and the medium. So we have been talking about body in terms of CL, CD, in terms of shape, in terms of area. But since it is the interaction between body and medium, we must also characterize the medium through which the airplane is flying. In this case, the airplane interacts with air, right? And we call that the airplane is flying in atmosphere, and that is why they are called atmospheric vehicle, unlike a space vehicle which travel most of its path in non-atmosphere, right? Okay, in space. But we will be restricting ourselves to atmospheric vehicle, and we are trying to know little bit about the atmosphere. Okay. This atmosphere is characterized for the purpose of interaction between airplane wing or airplane body with the atmosphere through three thermodynamic variables, that is pressure, temperature, and density. Right? After all, it is the force which comes because of the pressure. The temperature decides the density, and also density by itself will decide how much force actually the airplane will be experiencing for a given speed or for a given angle of attack. So we are trying to understand atmosphere through pressure, temperature, and density, and you will also know that we need additional information like what are the wind conditions there, whether the wind is 20 knots or 40 knots, heavy wind, low wind, what sort of humidity is there, or any other atmospheric attributes are there or not before you design an airplane for that flight corridor. Okay. And why we need to define something called standard atmosphere is also very simple and relevant. When we design an airplane, we go for a wind tunnel test, we go for a flight test. Then suppose we have designed two airplanes, we want to compare their performances. So suppose I am evaluating the performance of an airplane in Delhi atmosphere. Suppose I am same airplane I am using to evaluate its performance in Srinagar. So I cannot expect they will generate or they will experience same force for other conditions of speed, area being same. So when I want to compare two airplane performance, I need to compare them on a common platform or common atmospheric conditions. And that is why it is important that we define standard atmosphere through pressure, temperature, density, etc., so that whatever design we have made, whatever airplane we have configured, if I want to compare them, I will compare them assuming all the airplanes are flying in standard atmosphere, or what are their performances when I try to see them in standard atmosphere. Okay? Let us again come back. I need to know little bit on the altitudes. When I use the term altitude, we always think about the height from the surface of the earth. For all practical purpose, that is the height we refer to all the time. We also know by now that there is a height which is relevant from the center of the earth. For a space vehicle, etc., we are more bothered about its height from the center of the earth because we need to capture the gravitational force. Okay? So we'll define two types of height. One is HA, which we call absolute height, And we'll also define a height with respect to the Earth's surface, a g and hg, we'll say geometric height. And if I call this r, small r, as the radius of the Earth, then it is very simple to see HA is equal to hg plus radius of Earth, right? And we know that g at any station can be written as r by r plus hg square. The message is, if I know radius of Earth, if I know what geometric height I am, then, and if I know the local value of g at the surface of the Earth, which is g naught, or which technically we say sea level g naught, then depending upon hg, I can find out what is the value of g at a certain height, certain geometric height, hg. So that's not a problem. So we have defined two altitudes. One is hg, which is geometric. Another is HA, which is absolute. Right? Now you see the problem. The atmospheric properties like pressure, temperature, densities, they are not only function of altitudes at what height you are, but also function of whether it is day, whether it is night, which season it is, right? And so many other factors, maybe sun activity, right? So it is a very dynamic in nature. So very difficult to define a standard atmosphere based on local measurements. So what is done is, take measurements at different points, different places, and then make an average value, take an average values, and internationally everybody will agree that yes, this is the standard atmosphere we will be referring to when we are comparing two flight tests or two performances of two different airplanes. So the process is like this. What is done, that this data is generated through balloon. You know, there are weather balloon, they are launched, and it goes on sensing thermodynamic variables, primarily temperature, then sounding rockets, etc. Right? What we see classically, that temperature versus altitude. Typically, if you take the average values of all parts, most of the parts, relevant parts, and take the average, you will find the temperature with altitude, it will vary like this. If I come here, see, from up to, let's say, 11 kilometer, which is typically the tropopause, and most of our civilian airplane, jet engine airplane, they will fly at around that 11 kilometer tropopause. If I see here, up to 11 kilometer, the variation is linear, and the lapse rate A1 is approximately 6.5 into 10 to the power minus 3 degree Kelvin per meter, right? Similarly, the experimental observation shows that from 11 kilometer to around 25 kilometer, there is no change in temperature, and we call it isotherms, right? And again, beyond 25 kilometer to around 47 kilometer, it is having a gradient, but unlike in this region, this has a positive slope, and positive lapse rate, or we call it A2, is plus 3 into 10 to the power minus 3 degree Kelvin per meter. So this data, or this trend, is purely generated through experiments, through balloon, weather balloon, through sounding rockets at different places, different times, and some average value has been agreed upon by International Aviation Society. Okay. But please come back to our original question. Once I want to characterize the atmosphere, I need to know its thermodynamic variables, the pressure, temperature, densities. Temperature profile is here, so I need to know pressure and density, which is extremely important. If I want to find out lift, if I want to find out drag, these two thermodynamic variable will play important role. So I need to create a standard atmospheric model by using this experimental data. And how do I do that? That is done simply assuming that the air follows perfect gas law. That is P equal to rho RT. That is, we will be treating air following the perfect gas laws. And then we will be trying to find out what will, if I know the temperatures here, pressure here, density here, then what is the pressure, temperature, density at that point by using this in mind that they are perfect gas. Yeah, we are trying to develop a mathematical model, and we are assuming that this is element of air which is cubical shape with length 1 unit, breadth 1 unit, and the height dHg. Why Hg? Because Hg is relevant as far as atmospheric presence is concerned, right? So if I try to do a static balance, we know there will be a pressure acting upward the bottom surface. Let's say that is P. At the top it will be P plus dP. And also note here the weight of this fluid element. What will be the weight of the fluid element? Weight of the fluid element will be mass into local value of G. Mass is density into volume, so density is rho, volume is 1, length, breadth, dHg, and into G. This is the weight of the fluid element. And this weight is acting on unit area, because this weight is acting on unit area 1 into 1. So pressure because of this weight of fluid, in this case it is air, that will be rho G dHg, because area is 1. So now if I simplify this, I can write P is equal to P plus dP, P here, P plus dP acting down, and pressure because of the weight acting down. So I can equate them and find out that dP equal to minus rho G delta Hg. Okay. Now see here, there is a catch as far as operational part is concerned. If I clearly see that dP is minus rho G delta Hg, G is function of Hg. That is, as I am going up and up, the Hg, that is geometric height, is also increasing, and G also will become function of Hg. So if I want to integrate this to find pressure and all, so I have to know explicitly one thing, that G is not going to remain constant. In fact, to be more precise, the G should be also function of, H, HA, which is the absolute height, because as far as G is concerned, it is the reference is from the center of the earth. But since here dHg is there, you could see if G becomes function of Hg, then the integration becomes a little complex. So what is done for simplicity? Assume G is equal to G naught. That is, we are assuming that the value of G is what the value of G at sea level. Okay? That is constant. So now you could see for same differential pressure, I am writing minus rho G naught dH. For same differential pressure, I am writing minus rho G dHg. So definitely from this relation I can see that H and Hg are not same, and by geometry also we know H and Hg should not be same. Hg is because of the only because of consideration because of the atmosphere. So this geopotential height, this H, is defined as a fictitious altitude where I assume the value of G is not changing and you are taking as G naught. It is also at fictitious altitude and we call it geopotential altitude. As long as I know what is the relationship between H and Hg, I have no problem. I can revert it back, right? Okay. So to do that, you could see if I use these two relationships, I find that dH is equal to G by G naught into dHg. And since I know that G by G naught is nothing but R square by R plus Hg square, where R is the radius of Earth. So using these two relationship, I can write H equal to R plus Hg to Hg. Now, what is the error I am taking when I am assuming Hg and H are same? Just to have an idea, if you plug in the values, you will find at 65 kilometer, the error is just 1%. So you could understand assumption that H and Hg are same, that helps in making the analysis so simple. Still, you are getting the physics of the situation. Okay? So what is that important thing we have found out is, which will be rigorously used to model the atmosphere, is minus rho G naught dH. Okay? Now come back to this. What is our aim? Our aim is this temperature profile is available. I want to find out what is the temperature, which I know from here, what is the pressure, what is the density at this point, or some other point here, or some other point here. And what is given to us? I know what is the condition here. Right? From the static balance, what important relationship we got? We got dP equal to minus rho G naught dH, and H we have defined as a geopotential height, which is a fictitious height. But assuming that acceleration due to gravity is constant, and we have also seen that H and Hg hardly they differ. The error is around 1%, even at 65 kilometers. So we carry forward with this relationship, and also now you use the perfect gas relationship P equal to rho RT. So I divide dP by P, so I get rho G0 dH by rho RT. So I get a very important relationship, dP by P is equal to minus G0 by RT into dH. And you will see this will be used for getting the values of pressure and temperature at different points, right? Now we are taking the first case where this is the gradient region, that is the temperature is not constant. For example, here we are saying this is isotherm, that is temperature is constant, but here temperature is changing. So we will take how to find pressure, temperature and densities for gradient region, right? For example, if this condition is T1, P1, rho 1, if I know this, and I know A as the lapse rate, dH by dt, you could see for this region there is a lapse rate A1. So I can write T minus T1 divided by H minus H1, which is nothing but dt by dH is equal to A, which is lapse rate. So dH I can write as dt divided by A from this relationship. Once I write that, I can write dP by P. See here, dP by P is what? dP by P is rho G0 dH by rho RT. So now I substitute this dH by dH equal to dt by A. If I write that, then I get dP by P is equal to minus G0 RT into dH, right? So dP by P is minus G0 dH by RT. Here I will be using this relationship, that is dH is, from here I know by definition dH is dt by A, right? So I will replace this dH by this value to get dP by P is equal to minus G0 AR dt by T. Now you see, it's a very neat expression. I can integrate both sides, and I know G0 is constant, so I can write expression of P by P1 is equal to T by T1 to the power minus G0 by AR, and similarly rho by rho 1 is equal to T by T1 minus G0 AR plus 1, and of course we know T is T1 plus A H minus H1 through the lapse rate. So simple. I repeat again, I know this condition here, I use this relationship, and I just substitute dH equal to dt by A, I get an expression like this, I integrate, and I get the pressure, density and temperature for that point in the gradient region, right? Now, if I want to find out for the region where the temperature remain constant, which call isotherm, that is this region. Let's say this is the region. I know here again T1, P1, rho 1, this condition I know. I want to find out at this condition what is the value of temperature, pressure and densities. We are working towards the method to find out the thermodynamic variable, temperature, pressure and densities, the pressure and densities at different altitude, okay, given the initial condition T1, P1 and rho 1, right? So I again use like this, dP is equal to minus rho G0 dH. This we have derived from the static balance, assuming fluid element in static condition, and we have also derived this relation dP equal to minus G0 RT into dH, because we have assumed that air is behaving like a perfect gas. So P equal to rho RT, and I have divided dP by that, so I have got this relationship dP by P, okay? Where P is rho RT, that has been used here, P equal to rho RT, and we have divided dP by P to get this expression. This is done, right? Now if you see in the isotherm, I can simply integrate this. If I integrate both the sides, because temperature is constant in isotherm, it comes out. So what do I get? I get P by P1 is equal to e to the power minus G0 by RT into H minus H1. Similarly, I can find rho by rho 1 is equal to e to the power minus G0 by RT to H minus H1. So you could see in isotherm it is very straightforward. So what is the message? Message is, if I want to create the atmospheric description in terms of a thermodynamic variable, I need to identify whether we are looking in a region which is governed by the gradient or by the isotherm. And then I apply this relationship, and in practice you will find there will be standard atmosphere tables available. They are generated using this relationship, right? And of course, the standard value for pressure, temperature and density at sea level is a fixed number, and we all take that as the standard condition, that is at H equal to 0, it is PS, P standard is 1.01 325 into 10 to the power 5 Newton per meter square. Then density standard is 1.225 kg per meter cube. and temperature standard is 288.16 degree K. So this initial condition, the standard condition at h equal to 0, along with this relationship in gradient region and isotherm are sufficient enough to generate the whole standard atmosphere table. Okay? Why you have generated all these things, please understand, that should be very clear. That this standard atmosphere is required primarily to relate the performance of two aircraft, right? So that I can check their performance in a common reference. For all this, we are doing to address a question, which aircraft has got better performance?